Okay, welcome to class, everybody. We are into section 6.2. We're nearing the end of the material for the semester. We're just going to finish up chapter 6 about logarithms and inverses of exponentials. Last time around, we were introducing the idea of an exponential function, and we said it was any function of the following form, where a and b are just real numbers. And we saw that because of the fact that when anything raised to a power of 0, you get back 1, that the y-intercept here was at 0a. And we saw that this is what we were calling the base, and we got two different possibilities. The base was either a number between 0 and 1, or the base was a number that was bigger than 1. You couldn't be actually equal to 1, because then it was just what we were calling a constant function, a linear function. But the base had to be positive and in one of these two regions. This meant that the function was decreasing, or that there was exponential decrease, and this meant that there was exponential growth, or that the function was increasing. And the factor that you increase by is this actual b, right? So that's why we were calling it the base. And it's sort of really reliant on the fact that if you look at b to the x plus 1, it's the same thing as b to the x times b. So if you were to increase this exponent by 1, it's really the same thing as multiplying the output by b. So when you're thinking about this graphically, instead of like a rise over a run, like a linear function, here when you move one unit to the right, you should multiply by a factor, right? If that factor is in between 0 and 1, you decrease. If that factor is greater than 1, then you increase as you move to the right. Okay, so we're going to talk more about some of the basic features, the domain and the range of these guys, and then also about shifting them around. So we'll tie this back to some older material that we had covered previously on transformations. So again, our two main topics for today are to just now graph our exponential functions that we were looking at last time, and to graph exponential functions using transformations. And so as we lift these exponential functions off of the x-axis, we'll find that they're no longer exponential, but nonetheless, we can still analyze them using some of our previous techniques. Okay, so let me sort of show you the main features in Desmos of exponential functions. And then once we're done doing that, we'll come back and sort of summarize it here in the notes. And I'll give you some time to write down sort of the key pieces or the key features that we observed. Okay, so here is Desmos, and we're going to be looking at functions of the form f of x is equal to a times b to the power of x, right? And here when I say add a slider, what it's doing is just giving a value to a and b. Remember, b cannot be equal to 1, because if it is, all you get is something that looks like this horizontal line here, and that's just a line, right? So we have to make sure that b is either bigger than 1 or in between 0 and 1, and it also can't be negative, right? We saw that in the case when it was negative, the domain had some really sort of funky things happen, and so we either have a case where b is between 0 and 1, like over here, or when b is greater than 1, okay? And in those instances, it's telling you basically how much increase you have, right? So the larger this value of b is, the bigger the multiplying factor is, and the more growth that you have, right? So if we increase this base value by larger and larger amounts, the function grows steeper and steeper more quickly, okay? And the closer you get to 1, the sort of less steep it is, and you can do things, you know, like really, really close to 1, and you can see that it sort of lays down almost flat, but at some point, even that function blows up because it's an exponential, okay? So the closer you are to 1, the less sort of growth that you actually have, okay? Let's come back to something like this. And then on the other end, when you're a number that is in between 0 and 1, let's say like 0.75, then you're going to be decreasing as you go to the right. And that's because every time you multiply by 0.75, all you're doing is you're keeping 75% of the value that you already have, right? So right here, if I start out at 0, 1, and I multiply that y value by 0.75, I keep 75% of that, and I get to 1.75. And then 75% of that gets us to 2 and 0.563. Okay, and so it just keeps decreasing because you're multiplying by that factor of 0.75, and it's smaller. And the closer this number gets to 0, the more the decrease is, right? So the more quickly this would be decreasing as we go to the right. So if I were to type in a couple of extra zeros in there, you'd see that it almost would drop into an L sort of shape looking to it. Okay, so that's what's going on with that guy. And the closer that you get to, say, 1, and say 0.999, again, the flatter you get, but as you come back out and you zoom out, what you'll find is that it's still an exponential function, so you'll get that curve showing up at some point. I suppose we've maybe made it a little bit too, let's put it at 0.99. There we go. Okay, so in this case here, when you're at 0.99, you get that sort of curving out all the way at -500. Okay, so that's telling you what's going on with the b, right? So the value of b tells you if your exponential function is increasing or decreasing. Now, one other thing that you should recognize is that if a is positive, and for now we're just going to assume that a is positive in all of our examples. We're not going to really look at anything where the a is negative. So let me go ahead and clear that out for the moment so that a is not negative. But when a is positive and the b is also positive, this can never be negative, right? And you can see that in the graph because the graphs that you're looking at here will never drop below the x-axis, okay? So the fact that a times b to the x is positive means that this thing never drops below the x-axis. But you'll notice that it keeps getting closer and closer to the x-axis. And that's because, for example, let's think about what happens when b is a half, right? So when b is 1/2, and let's just say a is 4, just to make it a little more interesting. Let's go ahead and zoom in and think about what's happening as we move to the right. So here, when x is 0, we get 4. And then when we move to the right, we multiply by 1/2. So 4 times 1/2 is going to get us to this point here at 1, 2. And then multiplying by the y value by 1/2 again, we're going to get to the point 1, 1, and so on and so forth. And so as this value of x increases, this graph just gets closer and closer and closer to 0, okay? So what we're seeing here is that we stay above the x-axis, but we get closer and closer to it. And the way that we would say that is that we're seeing a horizontal asymptote. When the b is decreasing, the asymptote is as we move to the right. But when we get values of b that are bigger than 1, for example, here at 2, then the asymptote appears on the left-hand side as we go out to -infinity. Okay, so again, we're sort of seeing this idea about what's going on with the b, all right? Now, the last thing that I want to point out is what the a does. So let's look at the point 0a. And we should already sort of have a good idea of what a does. It's just a stretching or a squeezing factor. And when a is equal to 1, that would be the case when it's just b to the power of x. And b to the power of x is always going to have a y-intercept at 0, 1. As we increase the value of a, the graph gets stretched vertically. And as we decrease the value of a to something that's smaller than 1, it's going to get shrink down, right? So let's check that out. As we increase, it gets stretched out this direction. For example, if a is 5, it gets stretched out so that the y-axis is now up there at a value of 5. And if we go back in the other direction, we can go to numbers that are less than 1, and it gets then squeezed down to something like 0.75. And so now the y-axis gets squeezed down. So the value of a when it's positive is telling you how much stretching or squeezing is being done on the graph, okay? And pretty much as long as you have 2 points on the graph, if you can get, like, for example, this point and some other point on the graph, and you show that there's a horizontal asymptote at y = 0 in your picture, then that really is enough to sketch a exponential function. Okay, so now that I've shown you a few of these in Desmos, let's come back and just sort of summarize what I said, okay? And I'm going to give you guys a few moments to write this down, because it's basically what we were sort of looking at in those pictures. We're starting with our parent function as being b to the x. And we are going to multiply b to the x by a scaling factor of a. And again, here we're still in this scenario when a is greater than 0. When a is negative, we'll think about it in terms of reflections, but let's not get too far ahead of ourselves with reflections and just think about the stretching factor. And like I said, when the absolute value of a here, or when a is greater than 1, it got stretched vertically, right? It got the y-intercept increased from 0, 1 to whatever that new value of a was. And when a was less than 1, it got compressed down, right? So it got shrunk down. That 0a went down to something that was less than 1. We also then observed that there was a horizontal asymptote always at y equals 0. So you give me any exponential function, and there will be a horizontal asymptote at y equals 0. And the domain is just negative infinity to infinity. You can plug anything into b to the x, provided that the b is a positive number, right? We saw that when b was negative, you can get some really weird sort of stuff with complex numbers. But when b is positive, there's no issues like that, and the domain is negative infinity to infinity. And this is a really good thing to keep in mind for the final exam, because if somebody gives you an exponential function and asks you for the domain, you don't even have to really do any algebra or anything at all. You can just write down, it's negative infinity to infinity, right? You can plug anything into an exponential. Something that's a little bit harder is the range, right? And like we saw in these pictures that I was showing you here, the range included everything that was above the x-axis. And the way that you write out something that's above the x-axis when this a is positive is just all the numbers from 0 to infinity, right? So the range here is 0 to infinity. When the a is negative, we'll reflect things down below, and it'll be from negative infinity all the way up to 0. But here, we're just specifically talking about a is equal to a number bigger than 0. Okay, so I'm going to give everybody a moment to write some of this information down if they want to put it in their notes. And then once you've had enough time to write it down, or if you have a question, you can put it in the chat. But if you're ready to move on, just give me a thumbs up, and we'll move on to some questions like you might see in Infinity. Okay, so we've had a couple of thumbs up here. There's 13 of you, so I'll wait a little bit longer, just so give everybody a chance to really. Okay, and again, this is just a summary of what we were talking about in that graph, right? Some things that you should know. The A is the stretching and squeezing and telling you where the y-intercept is. You should always know there's a horizontal asymptote, and domain and range are pretty quick to get. Okay, and then how quickly the increase or decrease is depends on the value of B. All right, so here is a typical example of the type of thing you'll see in Infinity. They'll give you an exponential function and they'll ask you, okay, what's the domain range and the asymptote? That might be one variation of the question, or another might be like, here's 5 or 6 different graphs. You need to pick out which one is the graph of this function. On a final exam, when you have a piece of paper in front of you, we may ask you to actually sketch it out, right? So instead of picking out from a list of them, you may actually have to sit down and sketch it out. So that's what we'll do here. But the process that you do to sort of eliminate other things would be just sort of to sketch out the graph by hand anyway. Okay, so some of this is actually a little bit easier than the graph, right? So we can immediately write out the domain. What's the domain of this function? It's just a single interval like this. What do you guys think? We don't even need to graph it at all. We just need to recognize, okay, this is an exponential function. What's my domain? Yeah, it's just negative infinity to infinity because you can plug anything in for x, right? There's no need to take a square root or to divide by anything. Bam, so there's our domain. And then that a factor is positive, so that means our range is just everything above the x-axis, which is just 0 to infinity. And then finally, we should include this when we graph the function itself, but we should also know where the horizontal asymptote is. Because it's an exponential function, there's just a horizontal asymptote right at y is equal to 0. Okay? Again, the function that we're looking at here is f of x is equal to 4 times 1/2 to the power of x. So first off, is this function increasing or is it decreasing? We should be able to just look at this and say, where is it increasing, where is it decreasing? Okay, so Jordan is saying decreasing, Diane is saying decreasing, and the answer is, yeah, it is decreasing, and that's just because the base factor, this b, is 1/2. And so we should immediately see that it's decreasing. And it's decreasing by a factor of 1/2. When we move to the right by 1 unit, it should drop down by 1/2, right? When we move over 1 unit, it shouldn't move down 1/2 of a unit, but the whole thing, the output gets multiplied by 1/2, and it gets cut in half. So I'll draw that here in a second. Okay, so it's decreasing because that b is a positive number between 0 and 1. So that's another piece of information that we have. And we should also be able to write down the y-intercept pretty quickly as well. Just looking at the graph here, where is the y-intercept? What's the x and the y value? Yeah, so the x value is 0, the y value is 4. So we already know at least 1 point on the graph, right? And we know where a horizontal asymptote is. So we have a lot of information here about what the graph looks like. And typically, all you really need for an exponential function is maybe like 2 points, right? And once you have the 2 points, you can just sort of sketch in the general shape of an exponential. So here's one of them, 0, 4. So here's 1, 2, 3, 4. And we know that this point has to be on our graph of our exponential function. And you can think about it as the point where you'd plug in x is 0, right? So here, x is 0, 1/2 to the 0 is 1, so you get an output of 4. But you can just see that right from the graph. You know that that a value is 4. And you could think about it also as being sort of, it's a stretch, right? You stretched it from here up to 4, right? That multiplication by 4 stretches out the graph of 1/2 to the x. Okay, and then this factor of 1/2 means that when we go to the right by 1, we take this output, which is 4, and we multiply it by 1/2. So 4 times 1/2 is what? What should the output be here at 1? 2, yeah, so it cuts it in half, and we get to this value of 2. And you could have also thought about it as 4 times 1/2 to the power of 1, right? So 4 times 1/2, that's going to get you down to this value of 2. And then again, if we cut it in half again, we go from 2 to what? What should the output be over here for the 2? Well, not quite 0. We're going to cut it in half, right? So here, this distance from here to here is 2. If we cut it in half, what do we get to? Yeah, we get to 1, right? And then let's do 3, just so everybody's clear, right? So now it's this distance from here to here is 1. If we cut it in half, what do we get to over here at 3? What's this, the y value at 3? It's going to be 1/2, right? Okay. So the graph looks like this. As we move to the right by 1 unit, we multiply by 1/2, multiply by 1/2, multiply by 1/2. We just cut the height in half, right? And you can see that at each stage, this thing is positive, right? And it gets closer and closer to the x-axis, but it still stays above the x-axis. And so we've included the horizontal asymptote in the picture, and we've included the range in the picture, we've included the domain in the picture. And really, all we would have needed were these 2 points, right? We could have just taken those 2 points and then said, oh, there's a good sketch of our graph, okay? So really, like sort of 2 points is enough, provided you know it's increasing or decreasing and where that horizontal asymptote is. Okay, so that's this question here, right? Graph this guy, what's the domain, range, and the asymptote? Let's look at a slight variation of this problem. In this case, the A is 1/2, and now the B is 4. So slight variation on this. But pretty much most of the stuff here stays the same. So again, now we've got this a being 1/2 and the b being 4. So is this one increasing or decreasing? Yeah, it's increasing, right? So the b here is 4. So this b is 4. That's greater than 1, so it's increasing. This is exponential growth, and it's growing by a factor of 4 each time. Every time you move to the right, you multiply by 4. And then again, you move to the right by 1, you multiply by 4, right? So it's increasing by quite a bit, right? So this thing's going to increase by quite a bit. Where does it start out at? The y-intercept? The x value of the y-intercept is always 0, but what's the y value? 1/2, right? So we know that it's sort of like the regular 4 to the x exponential, but it's been sort of compressed down. So even though it's growing really fast, it's still been sort of cut in half at the very beginning, and that tells us where that 1/2 is. The domain, this is still good, right? The domain of every exponential is negative infinity to infinity. The range here, because the a is positive, well, it's still 0 to infinity. And certainly we still have our horizontal asymptote, right? This is never going to be negative. And when this value of x goes further and further to the left, like -1,000,000, we're going to get really close to 0. Okay, so let's go ahead and graph it, right? And like I said before, all you really need are basically 2 points. So let's say here's 1, here's 2. At 0, it has a value of 1/2. So we know that it goes through this point right here, okay? And then at x is equal to 1, what's the output? What do we get for the y value when x is 1? Well, so here's is 1, so it's 4 to the 1 times the 1/2 out here in the front. Don't forget the 1/2. Yeah, so we end up with a 2, right? So if we plug in x is 1, we get 1/2 times 4. Another way of thinking about it is this is 1/2, and then remember the multiplicative factor is 4, so a 1/2 times a 4 gives us 2, and it looks like this. And the only other piece of information that you really need to include in your sketch is just that this never goes below the x-axis because it's always positive. So that's what we mean by a horizontal asymptote, right? Be careful on an exam or something like that, or a quiz. If you see something that drops below the asymptote like that, then it's been a shift or something else is going on here. It's not an actual exponential function like this one up here. Okay, so we've just included where the y-intercept is, the domain, we know what the range is, we've included our understanding of the horizontal asymptote and the fact that it's increasing, and really it was enough to have like 2 points on the graph. You could figure out these 2 points in different ways, either by plugging in or thinking about it as multiplying by that factor of b. Okay, so it's another good example of graphing one of these guys and finding the domain, the range, and the horizontal asymptote. Now be a bit careful. If you may be thinking, okay, I just have to go through infinity and mark y equals 0 for every asymptote, but that's not quite correct because remember we're going to be thinking about transformations of exponentials as well. So we may want to shift this graph up by 2 units or down by 2 units or something like this, right? And then also, we've only been talking about when a is positive, but when a is negative, what's going to happen is we're going to reflect this whole graph across the x-axis, right? So we're going to replace, for example, 2 with -2 in the output. So there's also some issues here with reflection. But before we do that, let's go through, and I'm just going to graph 2 of these. I'm going to graph one that's increasing and one that's decreasing, but I'm going to sort of leave it as a choice for you guys, and I'll show you sort of how much information you need to include in your sketch. Again, the way that infinity will work is that it will probably give you several functions that, sort of have, graphs, and then tell you to pick the appropriate one, right? And you'll want to go through the same sort of analysis that we're going to do now. So let's put the decreasing functions on this side and the increasing functions on this side. Notice the a is still positive in all of these, so we haven't reflected across the x-axis. But which of these is increasing and which of these is decreasing? You can give me the numbers for the decreasing. Is it like 16, 15, and 18, or what are the numbers for the decreasing one first? Okay, so we've got 13, we've got 15, and we've got 18. Okay, and then what about the increasing guys? Okay, 14, 16, 17. Great. And this is correct, because all you do is look at the value of b, right? And here are the values of b. And you just check to see if the value of b is either bigger than 1 or between 0 and 1, right? And these ones here, the 0.69, are less than 1. So these are definitely decreasing. And then 15, 0.81 is decreasing as well. And here you can think about the 0.81 as being sort of, you know, that multiplicative factor. When you multiply by 0.81, you're keeping 81% of the original height on the function, right? Or the 0.69, you're keeping 69% of that function. So I'll graph one of them. Which one of these do you guys want me to graph? 13, 15, or 18? We'll just do one. Just the rest of them are pretty much the same. Okay, so we'll do 18. Over here. And then what about for the increasing ones? The reason they're increasing is they're bigger than 1, right? So 1.28, 1.28, 1.59. These you can think about as an increase in 28%, an increase by 28%, and an increase by 59%. So which one of those guys? 16 looks like. Okay, so we'll do 18 and 16. 18 here is this f of x is equal to 4 times 0.69 to the power of x. And then over here, 16, I guess, is 4 times 1.28 to the power of x. Okay. And I'm just so that, you know, things are a little bit different here, I'm going to call this one g of x, and we'll call this one f of x. And then that way we can move this stuff off the board, and we'll just focus on these two, okay? So here, you should realize again that this whole thing is decreasing. It should have a y horizontal asymptote at y equals 0, and the y-intercept is right here at 4. So here's 1, 2, 3, 4, okay? And then we can just think about what happens when we plug in 1. Well, when we plug in 1, we get 4 times 0.69. So we just need to take 4 times 0.69 and figure out what that is. Sorry guys, I think I got disconnected from you. But let's go ahead and do that, right? So somebody in the chat, let's figure out what f of 1 is in this case. It's 4 times 0.69. And again, it's 69% of 4. What do you guys get? Okay, so Ali got 2.76. And so here's 2.76 is a little bit closer to 3, so you put this second point here, and then you just draw this whole thing as decreasing, and it has a horizontal asymptote at y equals 0. So here would be a graph of, or a sketch of this graph, okay? Now on this second one, you're going to do the same thing over here. So here's 1, 2, 3, and 4. So we know it goes through the point 0, 4 because that a value is 4. We now know that this one is increasing. So what do we get in this case? What do we get for g of 1? It's going to be 4 times 1.28. We're increasing it by 28%. What do we get when we multiply those two together? Okay, Angelique's got 5.12. Okay, so we've got 5.12 here. So here's 5 up here, a little bit higher than that. It's up at this point like that. And then you just draw in your exponential function, so it passes through those 2 points, and you make sure it never drops below the x-axis. So it has a horizontal asymptote there at y equals 0. And the rest of these problems are done essentially in an identical manner, right? You just sort of check to see if it's increasing or decreasing you include the y-axis there, and then you include the y-intercept there, and then you include a second point, and just sort of sketch it in. And you make sure to include your y-intercept, or your horizontal asymptote. Okay, so stuff like that will show up. And again, I mean, it's not going to be exactly where you sketch it, but you have to sort of look through a graph and rule out certain features, right? And what you want to be looking for are things like horizontal asymptotes, where it's increasing, where it's decreasing, what's the y-intercept. You can rule out certain graphs just based off of the fact that they don't have the right properties. Yeah, Ali, it's a pretty easy section. There's not a whole lot of tough stuff here, but right now we can get back into some nice things with what we were looking at previously, okay? So now we want to talk about what happens when that A is negative. And when that A is negative, what happens is, for example, if you look at 2 to the x and you put in a -1 out in the front, then what's going to happen is you're basically just reflecting across the x-axis, right? So, for example, you're taking this point here at 4 and bringing it down to this point down here at -4. And so an increasing function with a negative A out in the front is going to then be a decreasing function. Okay, so this is a reflection around the x-axis, and we should be careful when we're sort of working these details with a exponential function. And then also as a reminder, we talked about flipping across the y-axis, and that's where we replace x, like 5, with -5. And so the formula just replaces x with -x. And what happens is you take this graph here like this in blue, and you reflect it across the y-axis over to here, this one in red, okay? One thing to notice here is that here the domain and range really hasn't been altered, but on this picture, when we reflect across the x-axis, the domain stays the same, but the range now flips to the negative numbers. So from -infinity all the way up to 0. So that's reflecting across the x and the y-axis, and then the A was the stretching and squeezing, and then there was one last set of transformations that we talked about that was moving things up and down and left and right. And the most important here is going to be translating things up and down, because what you'll do is you'll lift these horizontal asymptotes at y = 0 to a different spot, right? And so a vertical shift, either up or down of an exponential function leads to something that's no longer exponential, right? Because it doesn't have a horizontal asymptote at y = 0, it has it at a different location. And you'll have to take that into account when you're graphing transformations, okay? And we're going to do 2 different variations on this. We're going to sort of give a verbal description of a transformation. We'd like to graph it and write down the equation. And then we'll also look at a couple of examples where we give you the graph, and you'll want to, basically look at that graph, extract what the transformations are, and then write down the equation. So sort of two-way street, right? You can, take the function and graph it, or take the graph and write down the function. Okay, so let's start with something that's a little more verbal. Here we are describing a function, and we'd like to write down an equation for the described function. Furthermore, once we do that, we'd like to write down what's the horizontal asymptote for the function, if there is any, what's the domain, and then also what the range is. And here, because we're going to be doing some translations, things are going to be a little bit different, right? We have to be a little more careful about what's going on. Okay, so first off, we're going to start with the function f of x is e to the x. The e here is the Euler's constant. It's about 2.71. You should get familiar with where it is on your calculator before the final exam, because there should be several questions where they ask you to use e and evaluate e at various points. So if you don't know how to do that, you should sort of look up in your calculator's manual how to evaluate exponential functions. It will definitely save you some time. Okay, so let's start with that, and then we're going to go through this list of transformations, okay? So let's just graph that function f of x is equal to e to the x. So first off, where is the y-intercept of this function? What is the a value at this point? Give me the ordered pair for the y-intercept of e to the x. Not quite a third, so we're not really talking about any of the other information, just this one function here, f of x. So we're going to start with f of x first and then sort of draw the graphs as the transformations get done. So let's not take into account the transformations just yet, right? So I'm just talking about just f of x is e to the x. It's not going to be an e either. That's what happens at 1. Yeah, so a has a value of 1 here, so it just passes through the y-axis at 0, right? I'm sorry, at 0, 1, okay? So that point is going to be on there because f of 0 is 1, okay? Now, f of 1, on the other hand, is just e, and like we said, e is about 2.7, okay? So here, 2.7, here's 3, here's 1, it's going to be somewhere up here, right? And then it has a horizontal asymptote at the x-axis, and it looks like this. So there's our sketch of our first function, f of x is equal to e to the x. So that's the starting sort of parent function, right? That's the base function we start with. And then we're going to do several things. The first thing is we're going to compress it by a factor of 1/3. So we're going to just squeeze it down. And what that will do is it will take this 1 and switch it to having a y-intercept of 1/3, okay? So the new graph that we'll get when we do that is going to be f of x is equal to 1/3 times e to the x, okay? And that's taking the a value to be 1/3, and that just does this compression. So here would say, let's say like this was 1, this was 2, and this was 3. We're going to cut this value by 1/3, right? So it's going to go from 1 to 1/3 all the way down here. And then the same thing will happen here at 1, right? This number that was really close to 3 gets cut down by 1/3, so it's going to be slightly less than 1. And the graph just sort of gets smushed down, okay? That's that compression by a factor of 1/3. And it moves the y-intercept from 1 down to 1/3, okay? So now we've got through this first compression. Okay, now what I'm going to do in blue is the next piece here. We'd now like to reflect this across the x-axis. So we'd like to take this graph and reflect it down here to the x-axis. And you'll notice what that does is it takes something like this 1 and it turns it into -1, okay? So it puts the 1 here and drops it back down to a -1, and so the graph ends up looking like here's -1/3, here's something that's close to -1, and it'll drop down like that now, right? And the formula for that equation is going to be y equals 1/3 e to the x, and then we'll replace the a with its negative, right? So that's going to be -1/3. Okay, so again, we're taking this guy, compressing it by 1/3, and then reflecting it across the x-axis. And now we're at this formula, but that's not quite what we wanted. There's still a little bit more left to do, right? So we reflect it across the x-axis, and then we want to shift it down by 2 units. So what that's going to do is it's going to take the horizontal asymptote that we have here, and it's going to move it down 1, 2 units. Okay, so it's going to take this whole graph and shift it down 2 units. As I'm graphing it, why don't you guys type into the chat what the formula should actually be, right? So it's going to have this -1/3 e to the x, but an extra piece. What is the extra piece now? Well, be careful here. We're shifting down by 2, right? So we got to take into account the fact that we're going down. So the whole graph here of that horizontal asymptote now shifts down over here to y is equal to -2. Melissa has the right answer here. We just want to subtract 2 from our answer now, right? So this then blue graph is now going to just drop down by 2 units. This guy is going to drop down to here, and it'll look something like this, okay? And the formula for the final graph here is going to be y equals -1/3 e to the x. That's the compression by 1/3, the reflection across the x, and then down 2 units, okay? So again, the reflection about the x-axis, the compression by 1/3, and then moving down 2 units. So here's our formula for the graph that we're seeing here. And we still have to answer a few questions, right? So it was asking us for the domain, for the range, and the horizontal asymptote. And here is our horizontal asymptote, right? So this is not quite an exponential function because it doesn't have a horizontal asymptote at y equals 0. It has it at y equals -2. So it's been moved down by 2 units. The domain is pretty straightforward because you can, again, plug in anything. It's just -infinity to infinity. But really, we sort of need to look at the picture here in blue, right? This final picture here to figure out what the range is. What does the range look like? It's all the numbers that are below -2. Yeah, so it should be -infinity all the way up to -2. Okay? So here, once we graph this guy and we've gone through all the pieces of the transformation, we've got the horizontal asymptote, we've got the range, and we've got the domain, right? And we've got a nice little graph of it, right? So this point here is happening at 1/3 of a distance below -2. And then right here at 1, this is about at -3. And again, it's really just a sketch with most of these, right? So as long as your numbers are within reasonably, close answers, you should get full credit for a sketch. Okay. So that's that guy. And that's one direction, right? So giving the verbal description of the function and then graphing it, or giving the formula and then graphing it and asking some questions. But we can also sort of do it this way as well. So here we're given a graph, and we're saying that, well, the parent function in this case is 2 to the x. And we'd like to describe what has happened with these functions, right? What sort of transformations have been applied to 2 to the x. And once we figure out what all of the transformations are, we can then write down a formula for these 2 functions, okay? So let's start with this one over here. And the first thing that you should do with doing one like this, where it's a transformation of some exponential, is to identify where the new horizontal asymptote is. Because if you can identify the horizontal asymptote of this guy, that's telling you how much vertical shifting you have, either up or down. So for this first graph here on the left, where is my horizontal asymptote? Well, the -3 is the intercept, right? So that's going to be important as well. But here, we're talking about where is the horizontal asymptote. Okay, yeah, so it's up here at y is equal to 1, right? So if we look at this line right here, we can see that the graph is getting closer and closer as we go to the left to this function, or this line y equals 1. So that's telling us that that we're going to have a shift up by 1, right? So at the very end, the last piece of information that we can see here is that there's going to be a shift up by 1. And you should think about that for the one on the right as well, right? So let's not quite talk about it yet, but try to identify where that horizontal is. And that'll tell you how much shifting there's been up or down. So we know that this one's going to be shifted up by 1. But you'll notice that it's below the horizontal asymptote, right? And let me just, on the board really quickly, just sketch y equals 2 to the x to remind you of what it looks like. So y equals 2 to the x, when x is 0, it's going to give you a value of 1. And when x is 1, it's going to give you a value of 2. Right? So it just looks something like this. And if you carefully look at the picture on the left here in this question, that's not the same sort of shape, right? This one's increasing and going up. So it's a reflection, right? But what is the reflection of? Is it a reflection over the x-axis, the y-axis, or possibly both? What do you guys think? What are we reflecting across? So we're starting with this function up here, and we're going to reflect it across the x-axis to get a function that looks like that, right? Okay, so we know that we're moving up 1 unit. We know that we're reflecting across the x-axis. The next thing that we need to do is just determine how much of a stretch we have here, because in this picture that you're seeing here, the distance between the asymptote and the y-intercept is 1. However, over here, that's not the case, right? How far is this distance between the asymptote and the y-intercept? It's 4 in this case, yeah. So that means that we've stretched out our graph by 4 units, right? So we have to have stretched out our graph by 4 units. So let's now summarize sort of what I just said in a little more detail, right? So the first thing is we see that there's a reflection about the x-axis. That's going to get us from this graph sort of looking up like this to then looking down over here. The other piece of information that we saw was that there had to be a stretch, right? And in this case, the absolute value of A was 4, because we stretched it out by 4 units, okay? So we had to stretch that thing out by 4 units. And then finally, we saw that, I mean, if these were the only 2 things that we would have done, the horizontal asymptote would still be here along the x-axis. So the last thing that we saw was that we moved up by 1 unit. Okay, and let's go through each of these one by one so we can write down a formula for the function that we saw graphed earlier. Okay, remember, this is the function y equals 2 to the x, and we're going to first flip it across the x-axis. So that's going to give us y equals negative 2 to the x, right? Again, we replace the output of the function with its negative, and that flips it across the x-axis. And then here, because the absolute value of A was 4, we're going to stretch it by a factor of 4. So we just multiply everything by by 4, and that gives you negative 4 times 2 to the x. Okay? So just stretching everything out by a factor of 4, and that makes sure that this distance is no longer 1, but 4, right? And then the last thing that we want to do is add 1 to this, and so we get y is equal to negative 4 times 2 to the x plus 1. And here is the graph, or the formula for this graph that we were seeing here on the left, okay? So again, it's going to be negative 4 because there's a reflection and a stretch, and then 2 to the x, and then the plus 1. Okay, so that was that first one. Let's now look at the second one, and that'll be sort of the last thing we talk about today. Where is the horizontal asymptote for this one? What's the y value for the asymptote? So we're talking about this function over here now. Yeah, it's at y equals 3. Okay, so we're getting closer and closer to that value of 3 as we go this way. And again, you'll notice that it's not the same function as 2 to the x, right? So here's our graph of 2 to the x, and it's certainly not the same graph. But we can get that shape that we're seeing right there by doing a couple of reflections, right? So what do we need to reflect across? The x-axis, the y-axis, both. What are we doing? Okay, so if we were to reflect it across the y-axis, let me just show you the picture that we would get, right? So up here, if I reflect this whole thing around the y-axis, it ends up looking like this now, right? But let's go back to the picture with that thing. I mean, it's still, this shape doesn't really still look like that one, right? We've got to do both, right? We've got to both reflect across the y-axis and then reflect across the x-axis, right? Or we could also have thought about it as just, you know, reflecting across the x-axis to get this thing, and then reflecting across the y-axis again to get there. So we've got to do both, okay? So in this case, this is both a reflection across the x and the y-axis to get that shape that we're seeing there. And then we're moving up by 3. Okay, so the last thing that we really need to know is how much stretching did we do? And that's just basically going to be this distance from the y-intercept, the horizontal asymptote to the y-intercept. And how many units do we have there? What's that stretch going to be? 2. Yeah. So we're just stretching it out by 2. So instead of a distance of 1, like the normal 2 to the x function, we stretched it out by 2. So let's do the same sort of thing that we did before, and we'll just summarize the information that we just had, okay? So the first thing that we saw in our step was that we were reflecting across both the x-axis and the y-axis. Okay, and we were starting with the function y equals 2 to the x. So that was our parent function, or our starting function. We reflected it around the x and the y to get that same shape that we had over there. Then we saw that we had to stretch it by 2 in order to get that distance between the horizontal asymptote and the y-intercept to be correct, right? And that was just that distance we measured there. And then finally we said, okay, that horizontal asymptote was up there at y equals 3, so that means that we needed to shift up by 3 units. Okay, and let's just go ahead and do it step by step. First, reflecting across the x-axis, you would replace the function with its negative. Reflecting across the y-axis, you replace x with its negative. So if you want to do both, you just multiply the function by -1, and you replace x with -x. So that does this. That gets us into the right shape. Now we've got to stretch things by a factor of 2 because this would have had the wrong sort of distance. So we stretch it by a factor of 2, and we've got y equals -2 times 2 to the -x. Okay, so now we see that our a factor there is actually -2. And then finally, shifting it up by 3 units just means add 3 units to it. So this is y equals -2 times 2 to the -x plus 3. And there is our formula for that graph that we were looking at, right? And we obtain that formula by shifting. This is one of 2 different ways for obtaining some of these formulas. Another way of obtaining the formula is just to plug points in. So if you can see on the graph some various points, you can plug it in and sort of solve for the components piece by piece. But you can also sort of just look at the graphs and see what's been done with the transformation. Okay, and we're actually 3 minutes over, so I'm going to go ahead and stop the video and say thank you guys for being here.